Diffusion, the international science radio show.
We have a bouncer on the doors of perception.
The good, the bad, the ugly.
It gets pretty exciting.
The myths, the truths.
Toxicology.
Astroseismology.
Magnetism. The dark side.
Genetically engineered potatoes.
Planetoid.
Planetoid.
I love that word.
Hello and welcome to this special Exoplanet edition of Diffusion. Sit back and relax while we pilot you through time and space to land on another planet. I'm Ian Woolf. On this edition, Professor Chris Tinney talks about exoplanets, but first up, here's the news. Another Earth or not? Der Spiegel reports that the European Space Observatory at Mount La Silla in Chile has discovered an Earth-sized planet orbiting Proxima Centauri. The exoplanet is reported to be orbiting close enough to the red dwarf star for liquid water to be possible on its surface, which means life could be possible. The trouble is that Der Spiegel are relying on an anonymous source ahead of any announcements. The anonymous source is reported to say the official announcement is due at the end of August. When contacted by Agence France Presse, the European Space Observatory refused to confirm or deny the story. Proxima Centauri is just over 4 light-years away, making it, along with its companions Alpha Centauri A and B, the closest stars to Earth. It's a trinary system where the 3 stars orbit each other. They're close enough that you could get a probe there within a human lifetime. So if this announcement is true, it's huge news. Project Starshot, funded by a Russian billionaire, plans to send a tiny spacecraft to Alpha Centauri, powered by a laser from Earth aimed at a light-catching sail. They believe they could accelerate the spacecraft to reach Alpha Centauri in just 20 years. They may change the mission to include Proxima Centauri, depending on the announcement. Project Starshot is backed by Stephen Hawking and Mark Zuckerberg. The La Silla Mountain Observatory in Chile is the same European Space Observatory that announced the discovery of exoplanet Alpha Centauri BB back in 2012, which was also declared then to be the closest exoplanet to Earth. Unfortunately, later analysis cast doubts that it was real, and they concluded that it was just a mistake coming out of the data analysis. I'm guessing that this is why they won't confirm or deny the anonymous source. I think they're making very sure they know it's a real observation or not before they announce anything. If it's true, it's very exciting. Of course, just because it's warm enough for water doesn't mean there's any water there. Even if water is there, it still might not be suitable for life. We just have to wait until the end of August for the official announcement, then a few more years for the spacecraft to be launched, then another 20 years for it to arrive, some deceleration time, and then 4 more years to finally receive some pictures. Pictures, or it didn't happen. You're listening to Ian Woolf on Diffusion Science Radio. Send emails to science@diffusionradio.com. We're brought to you across Australia on the Community Radio Network and podcast over the internet on www.diffusionradio.com. Chris Tinney is a professor at the University of New South Wales. He heads the Exoplanetary Science Research Group. I visited him at his office and began by asking him, what is an exoplanet?
An exoplanet's just an abbreviation that astronomers use for an extrasolar planet. So it means a planet that orbits around a star other than our own. They were first announced in 1994, and that means that for anyone under the age of about 21, they've never lived in a universe in which there weren't planets known around other stars. For everyone over the age of 21, you would have grown up in a world in which the only planets we knew about were the planets in our own solar system. And necessarily, the discovery of exoplanets, or planets around other stars, has vastly improved our understanding of how planets in general form. And somewhat surprisingly, it looks like the way that the planets in our solar system formed is not necessarily the norm. It's not necessarily the most common type of planetary system out there in the universe.
So our solar system's a little unusual. So I guess I should ask you to tell me both how our solar system is different and what is normal or usual for the way planets form the way planets form around other stars.
Well, I don't know that we know exactly what's usual. What we do know is that when you've only got one example of a physical phenomena to look at, and you then build lots of theories around how that works, you tend to end up with a model that, not unsurprisingly, predicts exactly the features you see in your one example. So in our solar system, that means you've got most of the planets on roughly circular orbits, the rocky planets on the inside, the great big fluffy gas giant and ice giant planets on the outside, and all of those being more or less coplanar. And it was assumed, and all the models prior to about 1995 for how planets formed built systems just like that. What we've found from discovering exoplanets is that the thousands of exoplanets don't have properties like that. So the very first exoplanet we found was a gas giant planet not orbiting out at 5 astronomical units, 5 times the radius that the Earth orbits the Sun, where Jupiter is, but one orbiting in at a period of only 4 days, so well inside the orbit of Mercury. And none of the models for how you make planets could predict how you would make a gas giant planet that close to its star, and so the theorists had to run back and scratch around a bit, and they eventually came up with the conclusion that actually what happens is gas giant planets do still form out at very large distances, but there's a process called migration that takes place that allows planets to move from where they formed to where we found them. And that's a huge change. All of the models for how our solar system worked essentially said the planets form roughly where we find them. But it turns out that actually in extrasolar planetary systems, where you find the planets is almost certainly contingent on the past history of that planetary system. So the next lots of gas giant planets that we found over about the next 5 years, the number of them that were actually in nice circular orbits, like the planets in our solar system, was also rather small. Most of them were in eccentric orbits, so that is elongated elliptical orbits, not ellipses where the major and minor axes are the same size. And again, that's a surprise because all of the theories for planet formation, and indeed to this day pretty much all of the theories for planet formation, suggest that planets should form in more or less circular orbits. So how they get excited out of circular orbits into eccentric orbits, we don't quite know. It's possibly got to do with interactions of the planets as they evolve. It's possibly an outcome from migration of other planets within the system. So those are things, again, that the simple model didn't predict. NASA's Kepler satellite, which was launched about 5 years ago, and for just over 3 years did a survey looking to try and find Earth-like planets, so very small planets in roughly Earth-like 1-year orbits, has told us that small planets, not gas giant planets, but terrestrial mass planets and smaller, are actually very common in the universe. But even there we find them with a range of system architectures that's quite different from our own solar system. We now know of small closely packed systems of 5 or 6 planets, all well inside where just Venus and Mercury orbit in our own solar system. Now, all of which is not to say that planets, systems like our own, might not be common out there in the universe, but almost all of the planets we have found, largely possibly because of the selection biases in the searches that we use, don't necessarily look like our own solar system.
I've read in New Scientist in recent weeks theories about there being captured planets for our solar system that could have distorted the way that they are orbiting from what is more common.
So It's certainly true that we believe it's entirely possible that planets get ejected from systems as they're formed by dynamical interactions. And so there could well be planets sort of essentially what are sometimes referred to as free floating out there within the galaxy that are not actually stably orbiting around a star. And therefore it's potentially possible that those could be captured by another star later on in their history. And as I say, we know that planets move around. They don't just stay in one place. In our solar system, they may have stayed in one place. That may be why our system is stable and it is the way it is. But we know that in other systems, they clearly move around and they don't just stay where they form.
And how can we detect planets around other solar systems? Do we just see them in the telescopes?
No, unfortunately, finding planets is really hard. And so that's why the very earliest of science fiction writers in the Western canon, Giordano Bruno, a well-known mystic, heretic, and all-round fruitcake in around about 1600, predicted that there might be planets around other stars. But for around about the next 400 years, it remained a matter of science fiction because it's just really hard to see a planet around another star because planets are really, really, really dim and stars are really, really, really bright. Typical brightness ratios for an Earth-like planet to a Sun-like star are on the order of factors of 1 billion. And they sit right next to each other on the sky. And that means if you point a standard ground-based telescope or even a space telescope like the Hubble Space Telescope, the light from the planet and the light from the star basically are merged together in one blob of light, which is the resolution set by the ability of the telescope to see very fine detail. And so actually seeing planets around other stars is almost impossible. We have done that measurement for a handful of gas giant planets, but it's extremely difficult to do. The thousands of exoplanets that we have been found in by one of two indirect techniques. So not seeing the planet, but seeing the impact that the planet has on its star. So you can either look for the dimming that you get when a planet orbits across the face of its star along the line of sight to you. That's what's called transit detection. Or you can look for the gravitational force of the planet pulling on the star. Because planets don't just orbit stars. Stars and planets both orbit the center of mass of their combined system. And so stars have these very tiny orbits due to the planets going around them. And they produce a small wobble along the line of sight backwards and forwards, and by measuring the velocities of stars very precisely we can measure that wobble. So that Doppler wobble or the transit technique have been how we've detected the vast majority of the thousands of exoplanets we know about. And those two techniques both give us information. They don't let us see the planet and they don't let us see the light from the planet. But the transit technique tells us about the size of the planet, its physical dimensions, its diameter relative to the diameter of the star. And the Doppler wobble technique tells us about the mass of the planet. So that's the mass of the planet relative to the mass of the star. If you can do both of those things together, then if you know the size of something and the amount of matter in it, then you can measure its density. And that then allows you to determine whether a planet is gassy, like Jupiter, or icy like Neptune, or rocky like the Earth and Venus.
And how do you tell how close they are to their star?
Well, that simply comes out from Kepler's laws. Once you know the orbital period that a planet has, and you think you know the mass of the star, that tells you the separation between the two of them.
And so the big question for the science fiction fans is, can we find planets that might be in a habitable zone where life might form?
It is indeed the big question. It's also a very difficult question to do. Both the transit and the Doppler technique are really pushing the limits of what we can currently do to detect an Earth-like planet in an Earth-like orbit around a Sun-like star. That was actually the Kepler telescope's primary mission, and if it hadn't lost its second reaction wheel, which meant it was no longer able to point stably after about 3 years, if its mission had gone out to 5 years, then they would have been able to find a few examples. Even so, they've told us about what the likely frequency of Earth-like planets in Earth-like orbits around Sun-like stars is, and they're probably present around somewhere between 1 and 10% of Sun-like stars. But the real critical thing is that those Kepler detections are just that. They're just detections. They tell you there's a planet there, but for most of those Kepler objects, we can't go back and get more data that tells us more about the system. Because they're so faint, most of the stars that the Kepler mission found these very small planets around, we can't even go back and try to do the Doppler wobble experiment on them. So the next big thing for exoplanetary detection, the most exciting thing that's going to happen in the next couple of years, is the launch of NASA's next satellite called TESS, or the Transiting Exoplanet Survey Satellite. Now, whereas Kepler basically bored a hole in one place on the sky for 3 years and consequently had to look at faint stars in order to look at lots and lots of stars, the TESS mission has a different strategy, and it's actually got a much wider field of view, and it will be stepping around the whole sky. It'll do the whole southern hemisphere in its first 12 months of operation and the whole northern hemisphere in its second 12 months of operation. And I expect if it's still working, NASA will then flip it back over and it'll keep doing those for as many years as they can keep it going. And it will find thousands more extrasolar planets, but it will find them around stars somewhere between a factor of 10 and a factor of 100 times brighter. And that means for those stars, we can actually attempt to go and do the Doppler wobble follow-up. So we can actually try to say, what's the density of these planets? Are they rocky? Are they icy? The other key difference that TESS is doing is because it's looking at lots and lots of stars across the whole sky, it can target very faint stars. So the habitable zone is this sort of sometimes expressed as the Goldilocks zone. You want to be at the right separation from your host star so that you have liquid water at the surface. And if you get too hot, the water all evaporates and boils off, or you get a greenhouse like Venus. And if you're too far away, then the water all just freezes. Now, the Goldilocks zone for a sun-like star sits at around about 1 astronomical unit, 1 Earth orbital radius. Around a lower mass star, that shrinks in. And that's advantageous for a couple of reasons, because it means that the shrinking in makes the orbital period smaller, and it makes the Doppler wobble signature for a given mass planet much, much larger. And so it means that the TESS satellite is expected to find planets around up to hundreds of low mass stars. And those planets, if they're small enough, we can then go and follow up to find out whether they're sort of Earth-sized and Earth-massed, that is, that they're terrestrial planets with rocky surfaces, and that they may be at the right separation from their host star to be potentially habitable. So there's going to be a lot of development in the habitable planet space over the next few years. The exciting thing for Australia is that TESS is doing the southern hemisphere first. And so at UNSW, we're leading projects to build new facilities to go on the 4-metre Anglo-Australian telescope to actually do Doppler wobble measurements for the new potentially habitable zone planets that TESS is going to find. And we're also doing another experiment on another telescope up at Siding Spring Observatory called Funnelweb, which is going to be able to use a new technology for measuring spectra for all 3 million of the possible southern stars that TESS can look at. And that will then tell us about the properties of those stars. And that's critical because both the Doppler wobble and the transit technique tell you the properties of the planet relative to the properties of the star. So if you don't know the star, you can't know the planet. And so by having spectra for all of those host stars that TESS can find planets around in advance, it'll put Australia in the lead for both knowing which are the best ones to follow up to get the most high profile results, but also what are the properties of those stars so that we actually know what the masses and the densities of the planets are.
Can you also get spectra from any exoplanets to know what's in the atmosphere?
That's pretty much the sort of the holy grail. It's what we'd like to be able to do, but unscrambling the effects of the combined light, which is mostly what we see. In 20 years' time, we might have, there are ideas being proposed for space-based facilities that might be able to block out the light from the host star and see the planet even when they are so close together and have such a big brightness ratio. In the intervening period, what we get is the light from the two of them together. And so there are tricks you can play. The transit technique is usually used by just taking a picture of the star and a picture of some other stars in the region and just measuring the change of the brightness of the star in basically just a broadband filter. But if you can actually put a spectrograph down onto the host star while the transit's taking place, so you don't just get a picture, but you get a measurement of the flux as a function of wavelength coming from the star during the transit, then you can measure the transit depth as a function of wavelength. And the transit depth tells us about the radius of the planet, which is not quite the same thing as getting a spectrum of the planet, but it tells us about how the atmosphere of the planet shrinks and grows with wavelength, and that tells us about the chemical composition. Currently, those are very difficult experiments to do, and you can only really do them from space. But there's a new space telescope being launched called the James Webb Space Telescope in about 2018, and it will have new facilities for doing that sort of experiment. So I expect that TESS will deliver some of the very best candidates around the brightest stars for doing that unscrambling experiment to try and understand what the atmospheric properties are of both gas giant planets and potentially even smaller habitable type planets around other stars.
And if someone at school wants to go on to have a career studying exoplanets, what should they do?
Oh, well, mathematics, physics, chemistry, well, basically any science. Look, I often get asked what should people do if they want to become an astronomer, and my usual answer is, look, I don't care whether you become an astronomer. What I do care about is whether people are interested in science. So I don't care what sort of scientist you want to become. That's fine with me. Find an area of science that you're interested in and become obsessed about it, because that's sort of what I was when I was young. And my area of science I was obsessed in changed every couple of years. First I wanted to be a marine biologist. Then I realized I wasn't very good at putting my head underwater, so that wasn't going to work. Then I wanted to be a chemist. Then I wanted to be a physicist. And I eventually decided on physics and then moved into astronomy after I finished my undergraduate degree. It's a very exciting time to be working in this field and working in this field here in Australia. There's really going to be a tsunami of new exoplanets coming out from NASA's new satellites in the next couple of years. And because we're in the southern hemisphere, I think we're going to be in the box seat to get some of the most exciting results coming from that.
And you're speaking at the Powerhouse Museum next week?
Yes, so I'm speaking at the Powerhouse. Everything you ever wanted to know about exoplanets and how Australia is going to dominate the field on Wednesday, August the 17th at 6 p.m. Entry is free, although I think they do like you to register if at all possible on the Powerhouse website.
Professor Chris Tinney, thank you very much.
You're welcome.
That was Professor Chris Tinney, head of the University of New South Wales Exoplanetary Science Research Group, talking about exoplanets. Next up, here's Fred Watson with Why is Earth called Earth?
Why is the Earth called Earth? Well, mainly it's because it's what people have walked on since time immemorial. Had we evolved as creatures of the deep ocean, we might have called our planet water. Because once ancient peoples recognised that our world's a bounded spherical object rather than an infinitely large flattish thing, it was quite natural that the idea of the earth under your feet should be transferred to the name of the planet itself. Among all the planets, ours must have the least glamorous name. But for those of us who spend our lives contemplating far less appealing corners of the universe, it evokes warm sentiments of home as we consider just what a special place it is. Even so, there are some who complain that our planet's name is simply another word for dirt. And I'm afraid there's no denying that for the most part, that's exactly how we treat it.
You can hear more tracks from Fred Watson on his CD, An Alien Like You, at fredwatson.com.au. And that's all from us this week on Diffusion. Would you like to hear your voice on radio? We need more people contributing stories to Diffusion. Send your contributions, opinions, congratulations, standing ovations, helpful suggestions and donations to science@diffusionradio.com. That's science@diffusionradio.com, and please do send me an email so I know you're listening and you'd like to hear more episodes. Please like the Diffusion Science Radio page on Facebook and rate us on iTunes. Tell your friends. Follow me on Twitter @Ian Woolf. Check out the Patreon page, patreon.com/Diffusion Radio. Checking production was Charles Willock. I produced Diffusion, which is broadcast around Australia on the Community Radio Network, including 8CCC in Alice Springs and Tennant Creek, 2 NVR in Nambucca Valley, and 3 MBR in the Mallee Border districts of Victoria and South Australia. Diffusion is syndicated globally on the National Science Foundation's Science 360 internet radio station, and also on astronomy.fm. Subscribe to the podcast on the Diffusion website, www.diffusionradio.com. That's www.diffusionradio.com, and check the website for links, photos and videos about this week's show. If you enjoyed the show, then you can explore more than 850 previous episodes archived on diffusionradio.com, where the shows are labelled by keywords so you can focus in on the stories you want to hear. Subscribe to the Diffusion YouTube channel at youtube.com/c/diffusionradio. I'm Ian Woolf. Join us inside your audio device of choice for more science wondering next week on Diffusion Science Radio.